from the University of Lisbon, and she's going to talk about optimization of bodies with locally periodic microstructure by varying the shape, the topology, and the periodicity pattern.
Thank you very much, Felix. So I would like to thank the organizers for this invitation. I am very happy and very honored to present my work in such an iconic place. This is a joint work with Christian Barbarosia from the...
It's not very loud.
Not very loud, so...
In the front.
That's the right.
Yeah, because
the right reaction, but it should also go to
Perhaps a little louder. Don't know.
Just try now.
Okay. Thank you. It's better? Thank you. So this is a joint work with Christian Barbarosi from the same university and mathematical center. And there is something not going very well. Okay. So it's no. So I get inspired by real world, and real world is complex, and nature works through creating in each item materials adapted to optimally fulfill the necessary task for which they are designed to. And here are photos of, let's say, locally periodic structure in a cross-section of a banana leaf petiole. We have here a truss structure of a coconut leaf petiole, and if we take a zoom inside, we shall see periodic reinforcement in two orthogonal directions. And here there is a truss reinforcement in a dry physalis or Chinese lantern. So nature is smart, and we have to learn with it. Natural structures develop adapted internal patterns in order to be able to give an optimal response to external loads. In optimization via homogenization theory, in the context of linearized elasticity, we study bodies having locally periodic structure and optimize their microscopic properties. A body having a locally periodic structures has around each point of the body the material coefficients varying to a periodic pattern. And this pattern will change from point to point at the macroscopic scale. Homogenization theory allows one to accurately describe the macroscopic behavior of such a body by means of the cellular problems, which are elliptic PDEs in specific spaces that include periodicity conditions. So we shall present an algorithm that links the microscopic level with the macroscopic problem. At the microscopic level, we shall optimize following three directions: the shape optimization, topology optimization, and periodicity optimization. So we shall optimize the vectors defining the periodicity cell. The structure thus obtained has much more freedom to adapt itself to the macroscopic loads by adjusting the periodicity cell's aspect and orientation along the optimization process. And this is close to what we call free material design in some way. So what we'll do is to present gradient-based algorithm to optimize an objective functional with respect to the microscopic geometry. And for this goal, we shall need derivatives, so we shall need shape, topology, and periodicity derivatives. We shall extend these derivatives to the locally periodic microstructures and then give some details on the optimization process and finally some numerical examples. So we shall consider the periodicity cell defined in this general setting where three linearly independent vectors define this general parallelogram here in R3. It is important to state what is a y-periodic function in this context. So it's the function which here is invariant to translations, to entire translations with the vectors of the basis. And for a periodic microstructure, the rigidity tensor C will vary according to the periodic pattern, and it will be a y-periodic fourth order tensor. So here are the cellular problems in the way you can find in the books by Grégoire Allaire. And according to the homogenization theory, the macroscopic behavior of a body is described by the homogenized elastic tensor CH. So CH is defined in terms of the solution of this cellular problem we have here. And here we have the equilibrium equation and the periodicity condition, which states that the solution should be linear plus periodic. And the linearity is given by this macroscopic strain, which is a macroscopic strain matrix 3 by 3. And we have here the y-periodic part of this function. Epsilon represents the deformation, and C is the elastic tensor of the matrix material. The solution, the displacement solution WA depends linearly on the matrix A. And on this linearity is, we can prove, due to this linearity, that this effective stress also depends linearly on A. And this will allow us to define the homogenized elastic tensor from this average of stresses, of stresses, and also in type of energy products. We have the homogenized elastic tensor defined in this way for any two symmetric matrices A and B. And here we have considered graphic of function which is linear plus periodic. It's a space with, that is needed in order to well define the variational formulations of the cellular problem. A point about this is to note that any linear plus periodic function has kind of jump when we add the translations, entire translations with periodicity vectors. So we have here two different formulations of the cellular problem in stress and in strain, and these two formulations we have proven that are equivalent as long as we consider that this relation is fulfilled. Okay, so here we have the homogenized elastic tensor applied to the effective strain equal to the effective stress. So the macroscopic strain here may be expressed in terms of the inverse of the homogenized tensor, and this is what we call the homogenized compliance tensor. And as before, as we have done with the homogenized tensor, we can see here that in terms of energy products, we can define the homogenized compliance tensor in this way here. So we have proven in a previous work that these two formulations in stress and in strain are equivalent in the sense that the solution is the same, provided we have this relation between the effective stress and the effective strain. And conversely, we have the equivalent with the inverse of the homogenized elastic tensor. These are considerations which are important for the sequel. About porous materials, let's see the way we shall put mathematically the problem here. We shall consider infinitesimal perforations modeled by considering holes as compact sets included in the periodicity parallelogram cell. And we shall need to define special space in order to write down the cellular problems in this context, which is this perforated space. So it's the R3 from where we extract all the translations of the whole with vectors, entire vectors from entire coefficients from the translations, sorry, periodicity vectors, of the periodicity vectors, yeah. So here is how we write down the cellular problem in this context. It's what you can find in the books by Aller and so on. And the problem is the same, but we have here another condition which is linked to the existence of the whole. It's a Neumann boundary condition imposed on the boundary of the whole. The elastic tensor C is correspond to the base material and is considered to be constant. Note that here C might be anything, does not need to be is anisotropic. Okay. And we'll denote by LP perf the linear plus periodic functions defined in this R3 perforated space. So with this, in the context of porous materials, we have the strain formulation and the stress formulation adapted to this new context. So we have here new conditions. I don't have the time to enter inside, but we can prove also, we proved that they are equivalent. And the formula to obtain the homogenized elastic tensor are similar. The only difference is that now you are just integrating where you have material, so on Y except the whole. So the goal, our goal, is to optimize effective properties of a microstructure. And what we are doing is to minimize a linear combination of homogenized elastic coefficients. So here this is written in R2 for optimization in R2. We have here the coefficients of the linear combination, and F1, F2, and F3 is are elements form a basis of symmetric matrices. We are considering also volume constraint here and target volume V star given, and the volume is considered to be equal to the part with no hole over the whole periodicity cell. And we have a Lagrange multiplier. So the macrostructure will be optimal if its microstructure would adapt to give the best possible response to macro stresses and to macro strains. And along the optimization process, the microstructure will adapt by varying its periodicity, its shape, and its topology. And we shall see each one of these possibilities. So we shall deduce here the periodicity derivative by considering a transformation that takes this square, which square but may be anything, to this parallelogram. So what we transform are in fact the periodicity vectors that define each one of these two cells. And it's important here to suppose that this transformation is close to the identity, so it's equal to the identity plus a small variation. And in this case, we can ensure that V is invertible, having the determinant different of 0. And after computations, long computations, we obtained this formula for the derivative of the homogenized elastic tensor with respect to the periodicity pattern here with respect to this variation delta V. And note that this does not depend on the dimension. It is the same for 2 and for 3 dimensions. And also here C may be an anisotropic material for the basis material. And A and B are strain matrices here, arbitrary in their spaces. And choosing A and B in a basis of symmetric matrices, we can rewrite this periodicity derivative in this way, where P is a 6th order tensor that describes the sensitivity of CH with respect to this periodic pattern. And here is an animation that would like to give an idea about how the variation in periodicity influences the homogenized elastic tensor. About the shape derivative, I will not insist. This is the formula we are using here that we deduced. And this formula is valid for A and B, any matrices in strain matrices, so symmetric matrices. Note that this formula states for a base material which is isotropic with Lamé coefficients lambda and mu. And it is possible to write it in this compact form by choosing here two A and B in basis of symmetric matrices. Here S is a 4th order tensor that describes the shape sensitivity. And here is an animation to give an idea of how a variation in shape may influence the homogenized tensor. About the topological derivative, Here too, I will not insist, but here we have two different aspects of the formula for 2 dimensions and for 3 dimensions. Here also we have C, the base material, considered to be isotropic with Lamé coefficients lambda and mu. Okay. So, in the same way, the topological sensitivity may be written in this compact form, where T is a 4th order tensor describing the topological sensitivity of the homogenized coefficients. And here is our animation to give an idea of how this influences the homogenized tensor. And now about the optimization. Yeah, sure.
So this derivative is not so clear to me.
Yes.
How is it actually defined? I mean, what are you varying in the?
What I'm very, the topological derivative tests if it's appropriate or not to nucleate a new whole. So you have a whole and you are trying to understand if your design would like to have one more whole in order to minimize or to maximize the function you are optimizing.
And why is the position of the?
Y is another variable that has to do with the position inside the cell. Yes, yes, yes. I was not insisting because there are a lot of talks about this here. I wasn't really. Okay, but thank you for the question. Okay. So about the algorithm, we shall start with the initial microstructure, which is usually constant in the whole domain. And then we shall perform 3 steps, periodicity, shape, and topology until convergence. So all these steps have a similar structure in the sense that we shall solve the cellular problem, then we shall compute the corresponding derivative according to the formulae, and for the end, we shall change the periodicity or shape or topology according to the corresponding derivative. So and so on. So before explaining how it's done, the numerical implementation, I have to give some considerations about periodicity because they are linked, and only like this I can explain you how it's done the meshing. Okay, so about the periodicity, here is a periodic material and a square cell, but here we have the same periodicity. Let's say it's not the same periodicity, it's the same material but with another cell. You see? Here is a 45 degrees angle cell. And here is another arrangement different with this periodicity cell. And here we have the same arrangement in green with another periodicity cell, which this is a rhombic cell. So this is important to understand that two different generators may define the same periodicity group. So, and this is different of what we shall call a representative domain. So the periodicity cell is always a representative domain, but you will see that a representative domain may not be a periodicity cell. So what we mean by a representative domain is written down here. Is a compact set with first the property that its intersections with any of its translations from the periodicity group is negligible, And second, the union of all its translations from the periodicity group is equal to the whole plane R2. So let us see now the same arrangement in these four graphics, and here we have different the representative domains. And note that the only cell is this one, the rhombic one. And this is what is generally called in the literature hexagonal periodicity or honeycomb periodicity because of this. But this is not a cell, this is just a representative domain. And note that here we can understand by looking into the generators. So here we understand that the generators are the same. What differs is what we take inside to be the repetition of the same domain, the representative domain. Okay, so now I'm able to tell some more about what we are doing. We are considering periodic functions in R2 by identifying them with functions on the bidimensional torus defined as a quotient space. So the torus, as I say, is defined as a quotient space, is not this one which is drawn here, because this quotient space you are not able to draw because it is a surface which is not embedded in R3. Okay? So the quotient torus, although topologically isomorphic with the torus, is not isomorphic from the metric point of view. And the functions that are linear plus periodic may be identified with multifunctions on the quotient torus. And after a complete loop, the functions take values in an upper or lower range, creating foliations. Where you can see here that after a loop you are so you start from here. After a loop you are here, but then you are on a different foliation. And this is the linear plus periodic. So the linear part of the function makes this. Okay. Okay, so now I am able to speak a little bit about the finite elements for periodic elliptic problems as we see them. So what we meshed here is the quotient torus. What you can see here is the unfolded mesh. I'm not able to show you the mesh. I'm able just to show you the unfolded one, because the mesh is inside the computer and it is not possible to draw it. So here, only for visualization purposes, we drawn the unfolded mesh. Each segment that crosses the boundary here is drawn in blue or in this violet, and the boundary is not explicitly implemented. The boundary is implemented implicitly through the segments that are crossing it, and these segments are marked inside the code. Okay, so these segments that are crossing the boundary, let's say this one starts here, and this is the same segment that the one entering here. So these two nodes P and Q, they are neighbors on the mesh on the torus. Why? Because here Q star, this node here, which is fictitious in fact, is the same as Q. Okay, so this is how we are implemented the mesh on the quotient torus. And this unified treatment given to all segments crossing the boundary allows one to obtain this type of elongated holes, which are starting, let's say, here inside the cell, going out here, and then continuing on the other side, and getting out again here, and re-entering on this side. So here is the unfolded mesh, but here is the cell, how it's drawn. Okay. So let us see an example. The maximization of the shear modulus of the homogenized material. We'll start with a 60-degree periodicity cell. You can see here in gray the periodicity cell, and the algorithm will change this periodicity cell to a 45 degrees parallelogram. And let's see the animation of the optimization process. Okay, so here we have the 45 degrees parallelogram and the structure, the expected structure, let's say. And another detail is that we want to prevent extreme sharpening of the angles of the periodicity cell. So when the program, the code is facing with such a periodicity cell, then it will normalize it. That means it will choose among all possible equivalent cells the one which is closest to a rectangle by choosing the one of lowest perimeter. So we would prefer to use this type of cell, of course, by leaving the mesh unchanged. So, and let us see an example. Now it's a maximization of a convex combination between two young moduli of the homogenized material along the direction 2, 1, and its orthogonal 1, minus 2. And we'll start with a square periodicity, as you can see here. And the optimization algorithm changes the periodicity cell to a rectangle parallel to this direction 2, 1. So here it is. Okay. So now let's see this example of maximization of the bulk modulus. We are using here a rhombic periodicity cell. This is an example with no changing in the periodicity cell. It's a long process of alternate application of shape and topology. And note that new holes appear, and then they merge with the previous holes, and this is happening several times. And this gives the idea that there might be several solutions, because if we take a look here, if we take a look here in the history of convergence of the Lagrangian, except for the very first iterations, we have almost the same value, except for these peaks where we refine the mesh. Okay. So this is the enigma still to understand how all this material give the same, almost the same response. And here is another algorithm and another application. So this here we have the goal to obtain a material with a minimum Poisson coefficient in several directions of the plane. This is a new, let's say, work. Here we have to define what we mean by a Poisson coefficient when we are dealing with anisotropy. Because when we deal with isotropy, it's what we learn by books. But when we deal with anisotropy, you have to say in what direction you want your Poisson coefficient. And here V, it's an arbitrary direction, and nu V is the formula we found for the Poisson coefficient, depending here on of course of the direction V, and here with that tensor, which is the inverse of the homogenized elastic tensor, is the compliance tensor. Okay, here DH is the compliance tensor. And I will not enter in details, but this is a flow chart of an algorithm developed by Cristian Barbarossa and Sergiu Lopes, which is a minimax algorithm suited to make this type of optimization with several objective functionals in the same time. So let us see the numerical results. We will start with this initial guess, with this square periodicity, and we'll obtain this kind of a final design here. Here is the graphic of the Poisson ratio, and here we for these 8 angles, okay, 8 or 10, 10 angles, defined angles. So we considered from 0 to 180 degrees and divide this in 10 angles and consider each one of the directions and optimize at the same time these functionals, okay, coefficients. And here we have a zoom of the first 40 iterations and the zoom of the end 10 iterations. I think is right. Okay. Okay, here's another example with 60-degree cell, and here is what we obtained. I think I have here, yes, an animation to understand how the optimization process makes this whole to have that strange aspect. Okay. Note that here we allowed for topology optimization, but it doesn't feel always to do it. So we allow, but sometimes most of the times he does not. Okay, here is the graphics for the 18 directions chosen, and here is a zoom of the first 40 and the zoom of the last ones. Okay. Okay, and let us go now to locally periodic microstructure, because our, let's say, main objective is to make the link macro-micro. This is the so I shall not enter here into details. It's just to say that the cellular problem, when we have local periodicity, would depend on both two variables, the x variable, which is the macroscopic one, and the y variable, which is the variable in the cell. So everything happens in the same way, except we have to pay attention to this new variable. Okay. The formula apply for locally periodic, so for porous, local porous materials. Okay, and here is our problem at the macroscopic body. The equilibrium equation Dirichlet condition and a Neumann condition. Okay, so and here we'll have the homogenized material that is linked to all those cellular problems. Okay, so we shall perform here periodicity, shape, and topology optimization within this problem by optimizing in these cases compliance, but we could optimize any other function. So we will impose also a constraint on the volume, and here the volume is the integral of the local densities, and the local density is equal to this local volume. Okay. Okay, how it works? So we have this chain of dependencies for the holes T of X. For each hole, we have the corresponding homogenized material CH obtained by this formula. Then with this we compute the displacement, the state equation, the macroscopic displacement, and then we enter with it in the functional, the cost functional we have to minimize or maximize, depends. Okay, so these are details of how we are doing it. Of course, as before, it's a gradient-based method, so we'll need to derivatives, and we shall need the the shape derivative, the topology derivative, and the periodicity derivative itself. Okay, we have here. So the optimization algorithm will do all this at the cellular level. Let's say it's not at each point. In every finite macro-finite element of the structure. So this is the optimization process. We start with a globally periodic structure. We compute the homogenized elastic coefficients and the material densities and solve the macroscopic elastic problem, compute these sensitivities, and then we are going to perform at the cell level all this optimization and to try for the convergence and so on. Okay, so here are some implementation details. Here is our macroscopic mesh. It is done with rectangles, but it could be done with triangles or so on. In each macroscopic finite element, the microgeometry is supposed to be constant, so consequently the homogenized elastic tensor and the material density are constant here. And in each one of these macroscopic finite element, we have the cellular microscopic structure characterized by this cellular problem, by this cellular structure, and here we have the mesh, a triangular mesh, which I have presented at the time. Okay. So this is done by controlled by a Python script. It's necessary because we parallelize these computations at the microscopic level may go on all at the same time, and so for the macroscopic analysis, it's done in C++. In let's say our in work Manifem code. It's a C++ library, homemade, and it's under construction, and we would like to deal with three-dimensional periodic homogenization problem. It deals till now with two-dimensional periodic homogenization problem, and the point is that it will work with manifolds which are not embeddable in R3, like the quotient torus, and it will easily define variational formulations as C++ objects. And let us finally see some numerical examples. Here we have a cantilever with the proportion 1.51 clamped on the left side and subject to loads on the right side with this structure, and we minimize compliance plus here the constraint on the volume, and here we have the type of the mesh. Here we have 1,000 to 2,000 triangles in each one of these 600 Lagrange finite elements, and the base material is isotropic with these characteristics. And here is the initial gas. It is in each finite element here has this structure. Okay. And now this is what we obtain. We can see here some examples of what happens in each one of these points. And here is the history of the Lagrangian. In green is another computation without periodicity. So here in red is with periodicity. We can minimize until here, and without periodicity we were just here. Okay. And now I would like to show you something which is important. Yeah. Okay, so here you can look to this on the internet. It's always there, and here you can see in every of these cells what is happening. Okay, okay. So now the other example. So the same cantilever, but here with the load on the lower corner. And the final design here, okay. We can see here the history of convergence, and also we have this. Okay. And another example here. Here we minimize this convex combination of compliances that correspond to these three loads, okay, and this is the final design. We noted that in all these designs, practically the topological derivative does nothing. It is allowed to do, but it does nothing. But it's funny that here is in a certain point we saw here a nucleation of the whole, and probably if we would continue the iterations, we would observe that it disappears. So it appears, it is trying, but it doesn't feel necessary to do it. Okay. Okay. And now our last example on L-shaped two-dimensional body in proportions 2:1. Is clamped on the upper side, and it has this concentrated force here. Is divided in 2028 Lagrange finite elements Q9, and here is the final design. Here are two examples of meshes in these 2 points, microstructures, And okay, here are the Lagrangian, the compliance and the volume histories, and we can see here, okay, the same thing. Okay, can see here the whole structure, how it's happening. Here's not void. Here it's just it feels like making void, but he cannot because we have the cell. Okay. Okay. So thank you very much for your attention.
So since you're only minimizing the compliance plus the volume, or on a volume constraint, I was wondering why you don't see any microstructure within each periodicity cell. Well, is that just because your volume is so low that you just need one microstructure scale, or is there a different reason?
I didn't understand. So
typically, I mean, by optimizing the topology within one periodicity cell, you optimize the homogenized elasticity tensor.
yes.
I would expect that if that a certain homogenized elasticity tensor would be optimal, that you would need two different scales to achieve that.
Oh, yes, I understand. No, here, in fact, there is one example. You mean a rank?
Yeah.
Yeah, sure. Yeah, there is here an example. You know, you see this. For me, this is kind of rank.
I see. But okay, but why is this? I mean, it chooses a particular scale. Well, how does that come? Is there an additional regularization inside? Why are those not infinitely small?
No, because you have first the topology, and then the topology is only to nucleate a small hole. The topology derivative deals only with small holes. Then you come with the shape derivative, and this is inflates your hole, or it makes it disappear.
Okay, so I see. So that means what you're saying is if you iterate more and more, so
yes,
first do topology optimization, then you do shape optimization. And
yes, yeah,
introduce
yeah.
more and more holes, and you just stop at some point. Yeah, and that's then.
In fact, how we do it is we have one iteration of topology, and then we come with a shape for 10 iterations also, and then another topology iteration, one, and then another shape. And the periodicity, I think we are checking every iteration. So it's one of topology or shape and periodicity afterwards, because you need to adapt the direction. It's how it works. Because in my opinion, the way you are deducing the topology derivative from the let's say rigorous point of view, this works only with infinitesimal holes. And in practice, the whole, you have to take out one node of the mesh. So you have to make a hole which is small, but it will never be infinitesimal. And then afterwards, you just use the shape, because this, I think, is good inside the mathematical conditions.
Yeah, so I guess you're using standard geometric optimization in the cell, so you must have somewhere in your code a minimal size of your mesh.
Yes.
Periodicity cell, so that's why you have a finite length at some point, no?
Yes. Yes, there is a, yeah. We are starting with a mesh, and then we iterate with this one, and afterwards we are just cutting in two long segments. So choosing 4 long segments and cutting and so on. Yes. Yeah.
I didn't understand very well how you perform and what is the renormalization of the periodicity cell.
Yes. How it performs. Yeah.
How it is performed and what it does exactly.
How is this performed? It checks for the perimeter of the cell.
Yeah, but
and then you understand what are the it's a lot of geometry, differential geometry inside the code. So you are just understanding. As soon as you understand what are your vectors that define the cell, you have everything.
Okay, so basically you try to find new generators.
No, the generators are the same. You just try to make combination of these generators. Yeah.
Okay. Then in this case, I would have expect something that, because as the previous remark, the best is to construct something like that should look like rank 2 laminates. So what I would expect is that it will be normal. Your cells should degenerate by.
They are not allowed to degenerate because of the mesh. When they would degenerate, but we stop the program just there. You understand? Because you have a mesh. The most let's say elongated things you can admit are these. So here you have this type of mesh. You cannot have more than this.
No, but it's not. I think that's the question is different. It's not about the degeneration of the kind of
no,
but it's the degeneration of the periodic cell.
Could be very
of the periodic cell. No, but
Something like
we are checking. We are checking from time to time this.
But they should be very flat in one direction.
Yes.
And when you renormalize, you will change your periodicity cell and then add up a lot of periodicity cells, one on the top of the other, in order to obtain something that looks more like a square cell. And then, but the mesh of your cell will be, in this case, very, very big because you have different.
No, so it was this example here. I had this. So this going to extreme. I mean.
No, it's not the extreme I was
thinking. Yeah.
So, for instance, can you explain a little bit more what you are doing on this example?
Yes, the mesh is the same. Okay, the mesh is the same, and when the code is facing with such a, let's say, such a cell in the figures B or C, then it will change to the other one because the vectors are the same. Okay. The periodicity vectors are the same, and it will try to minimize the perimeter. To minimize, to choose the smallest perimeter, it's possible.
Okay.
So, yeah.
I just have to add one small point. I think the difference between rank 2 and like a rectangular unit cell is very small in performance. It's like on the range of 1%.
Yeah.
So that's probably why you don't see it going to more like a rank 2 like structure, because the difference is so small.
Yeah, but here just to say, here we have only 2 scales. Rank 2 is 3 scales, so we don't have this. We just have 2.
Just a small remark. This problem that you're discussing here on this slide of redefining the unit cell so the periodicity is exactly the same is quite standard problem in problems in which the periodicity is changing in time, and your unit cell can get very elongated.
Yes.
But the usual way to deal with that does not involve minimizing the perimeter. That's a quite unusual. It's not even clear to me that minimizing the perimeter will give you a fat unit cell.
I think no. It's a problem. I think it's not difficult to solve. I was thinking about you just take a parallelogram, a general one, and then you just minimize perimeter and you find a rectangle.
Yeah, okay, okay. If that works, great. I just thought it's not the usual criterion.
For here it works.
Yeah.
I don't know for.
Big one?
Yeah, so your cell is varying from point to point in the last example that you showed. Have you tried to see if they can be connected nicely? Because, you zoom and you have a nice cell, you zoom at some other point, you have another nice cell, but do they connect regularly, for example?
No, of course not. No, because the idea is like a patchwork. The idea is that here you have the you have to pass to the limit first into the micro mesh, and then you just glue everything together. But it's no. It's not like in the photo of the cross section of the banana leaf. No.
I'd like to ask, I didn't understand which part is integrated in the performant domain and which part is integrated in the Y domain. Is it the sensitivities are computed, when you compute the sensitivities, the integrals are computed in the just the solid domain, and the homogenization is still considers the wholes?
So the derivatives, you mean, yes. Where are they computed?
Yes, the integration domain for the.
So if you are making a minimization at the micro level, it's in the cell. If you are making optimization of the macro scale, it's always on the cell. It's always on the cell here in this yeah.
That means the solids.
No, the cell means for each. Let's say for each macro finite element, it's computed inside the corresponding cell. So for each finite macro element, okay, then you'll have a cellular problem, and there you make all your computations. You're welcome.
I have a question. So,
Yeah.
also about this optimization in the period. So I suppose, especially in the three-dimensional case, that must relate to what people do when they try to optimize the lattice structure.
Yes.
In
Yeah.
metals, for instance, when
Yeah.
they want to know which type of grid, which type of lattice is the best type of lattice. And in a certain sense, the space of lattices itself has a kind of complicated topology. You expect several local minimizers. So people might have thought about how to kind of avoid the pitfalls of being stuck in a local minimizer in this situation. Have you looked at this?
Not yet. Not yet. But thank you for giving me a light for where to start it. No, not yet.
Yeah,
No.
I don't know. I mean, more questions? Okay, so thank you again.
Thank you very much.